So we begin with chapter 3, section 11 of L&L's classical mechanics, and this section is titled Motion in One Dimension. The motion of a system having one degree of freedom is said to take place in one dimension. The most general form of the Lagrangian of such a system in fixed coordinates is L equals 1/2 A of q dot squared minus u of q, where a of q is some function of the generalized coordinates q. In particular, if q is in Cartesian coordinates, let's say x, then we have L equals 1/2 mx dot squared minus u. And the equations of motion corresponding to these Lagrangians can be integrated in a general form. It's not even necessary to write down the equation of motion. We can first start from the integral of this equation, which gives the law of conservation of energy. For the Lagrangian, we have 1/2 mx dot squared plus u of x equals e. So we have e equals 1/2 mx dot squared plus u. And this is a first order differential equation and can be integrated immediately. So if we rearrange here, we get e minus u equals 1/2 mx dot squared. So we will have x dot squared equals 2 over m e minus u. Taking the square root of both sides, we get x dot is equal to 2 over m e minus u. And from here, we can notice that it is a first order differential equation if we write it as dx over dt equals 2 over m e minus u. We can use the method of separation of variables to get dx over the square root of 2 over m e minus u is equal to dt. And if our particle were to be, for example, we're calculating the length of a pendulum, right? If this is our starting position, I'll call that phi naught, and this would be phi 1. And we can see that the pendulum will traverse here, and it will traverse back to a negative phi 1, and then back to phi naught. Thus, we get that our period is 2t1, or 2 times the time it takes to get from phi naught to phi 1. So we can implement that into our integration. So we will get 2 times the square root of 2 over m dx over the square root of e minus u. And taking the 2 inside of the square root, we can just get 4m over 2 square root. And all of this simplifies to the square root of 2m dx over the square root of e minus u. It will be equal to dt. Now, the two arbitrary constants in the solutions of the equation of motion are represented by the total energy and the constant of integration. Since the kinetic energy is essentially positive, the total energy always exceeds the potential energy. So the total energy is always greater than the potential. For example, if we let the function u be of the form which is here, which is just a function of x, then we can see that if we draw a figure in a horizontal line corresponding to the given value of the total energy, we can immediately find the possible regions of motion. So if our function of u, this would be much easier to show with a graph. If our function of u is like something like this curve here, right, we can see that in this points here, these 2 points here, I'll call them x1 and x2. We can see that it sort of makes a potential well, in essence, that if I call this line here E, it's that U must always be less than E. So this indicates that if at any point U equals E, then this would give the limits of the motion, because from here, if it were to equal E, we can see that the particle would traverse over the hill and begin to move down. Then thus we can say that when U equals E, we get our limits of the motion. And these are also going to be known as turning points of the system. A finite motion in one dimension that is oscillatory, the particle moving repeatedly back and forth between the 2 points in this potential well has a period t of the oscillations that the time during which the particle passes from x1 to and back is twice the time from x1 to 2. So this is kind of giving the example that I gave with the pendulum earlier. As the particle moves to point 1, then back to point -1, and then back to the origin, this would just be twice the length of the period. And that's pretty much all L&L was saying with this section. He does give an example, a problem actually, to determine the period of oscillations of a simple pendulum. And I will be doing that in the next video.